Good afternoon, class. Here's exam 2 review, chapter 3, differentiation rules. Exam 2 covers from 3.1 to 3.8. Here's 3.7, rates of change in the natural and social sciences. Section 3.8, exponential growth and decay. Reminding you of what we did last, which was differentiating logs, and to do so, we are going to use logarithmic properties to expand the log first and foremost. So, for example, the product rule, log x, y is log x plus log y, all of them have the same base. So, we're going to expand this. We get ln of 3 plus ln of x, and this piece becomes 5 ln of x plus 4. I'm hoping no one has any problem with that. And now ln3 is a number. When I differentiate, I get 0. Ln x is 1 over x, reminding you that the derivative of ln x, just flip it over. And now this one plus 5. Again, ln of g of x. Flip this over, 1 over x plus 4. And then times g prime by the chain rule, which is the derivative of the parentheses happen to be 1. So what we are looking at is 1 over x plus 5 over x plus 4. And again, this is the only calculus step, everybody. And now, obviously, the LC, the common denominator is x times x plus 4. So we have 1 times x plus 4 plus 5 times x. So 1 times x plus 4 plus 5 times x. And it's x plus 4. And we have 6x plus 4 over x times x plus 4 as the final answer. And now rates of change. It's exactly the same thing we've seen. Rise, the concept of a rise over run is known as the difference quotient. Delta y over delta x. Or f of x up 2 minus f of x up 1 over x up 2 minus x up 1. Delta x is the run, delta y is the rise. Now delta y, you can say f of x up 2 minus f of x up. It's called the average rate of change of y, or f of x with respect to x over the interval of x up 1 to x up 2, and can be interpreted as the slope of the blue line, which is known as the secant line. We recognize the following limit as being the derivative f prime at x sub 1. So instantaneous rate of change, limit of delta y over delta x as delta x approaches 0. Limit of f of x up 2 minus f of x sub 1 over x up 2 minus x sub 1 as x up 2 approaches x sub 1. X up 2 approaching x sub 1. Limit of f of x minus f of a over x minus a as x approaches a. If this is x, and this is a, and this is x, for example. Limit of f of a plus h minus f of a over h as h approaches 0. So if this is a, let me just write that. So there are different ways of doing that. If this is a, and this is, for example, h, then that's what we get. Or if it's x, we get this one. Okay, so they all mean absolutely the same thing. So f prime at a is limit of f of x minus f of a over x minus a as x approaches a, or limit of f of a plus h minus f of a over h as h approaches 0. Average rate of change, my work. Average rate of change, m of pq. Instantaneous rate of change, m of tangent line. That's all there is to it. So the derivative f prime of a is the instantaneous rate of change of y, or f of x with respect to x when x equals it. Just to remind you the good old differentiation formula. So having said that, let's look at the simple example. Find each of the following, where the cost function is 62x squared plus 27,500, and revenue function is x cubed minus 12x squared plus 4dx plus 10. So we're going to start with elementary algebra. What is the profit? As you know, profit by definition is revenue minus cost. So the difference between the two. So revenue minus cost. Okay, so x cubed minus 12x squared plus 4dx plus 10 minus that one will result in x cubed minus 74x squared plus 4dx minus 27,490. Now, let's find the total cost, revenue, and profit from the production and sale of 50 units. Elementary algebra. So replace the x in each case with number 50. So C of 50. Let's replace it right here. Put it into a calculator. 62 times 50 squared plus 27,500 gives you 182,500. R of 50, plug in 50 cubed minus 12 times 50 squared plus 40 times 50 plus 10, and that gives you $97,010. Profit function. Now, this can be done two ways. One is just plug it in here. That means 50 cubed minus 74 times 50 squared plus 4 times 50 minus 27,490. And that gives you $85,409. However, you really don't have to do that. The fastest and easiest way would be just by definition, if P is R minus C, then P of 50 is R of 50 minus C of 50. R of 50, which is this number, minus C of 50. That's it. And you can try it. Of course, I just wanted to show you there are two ways. This should have shown up first. It didn't. The marginal cost, revenue, and profit when 50 units are produced and sold. The marginal cost in business, the word marginal refers to differentiation. Okay. So marginal cost, that means C prime of X. Okay. Marginal revenue, that means R prime. Marginal profit, that means P prime. So having said that, C prime, 62 times 2, 124x. C prime of 50. Now plug in 50, evaluate it, 124 times 50, and we get $6,200. R prime of X, differentiate this, you get 3x squared minus 24x plus 40, and now plug in 50. 3 times 50 squared minus 24 times 50 plus 40, and putting it in the calculator gives us 6340. Now P prime, again, two ways. 3x squared minus 140x minus 148x, I mean, 2 times 74, right? With a negative sign, plus 40. And now evaluate it at 50, which means 3 times 50 squared minus 148 times 50 plus 40. You come up with the answer. And needless to say, P prime is R prime of 50 minus C prime of 50. So this is 140, and this is the second method to do that. Even here, P prime is R prime minus C prime. So you can subtract 124x from here. And that gives you 3x squared minus 24, and minus 124 gives you minus 140x. So 48x. So you could do that. Now, so when 50 units have been made, The approximate cost of the next unit, the 51st unit, will be $6,200. So this is the significance of this. If I want to calculate the cost for the next unit precisely, C of 51st is C of 51 minus C of 50. In other words, the cost function, plug in 51 minus plug in 50, and the answer it gives you, it is extremely close to this number. C of 51 minus C of 50. When we go through the process, 62, 62. So take a look at this number and compare it to this number, or as it's put here. Clearly, they are almost identical, but clearly this is easier to calculate. That's the significance of that. Same thing for R prime of 50. The approximate revenue from the sale of the 51st unit will be about 63.40. For an approximate profit of the 51st unit of P prime of 50, which is $140. So that's the importance of the marginal cost, revenue, and profit. If you plug in any number, it shows the value for cost, revenue, or profit of the next unit. The distance in meters of an object from a starting point is given by S of t equals 2t squared minus 5t plus 40, where t is time in seconds. What is the velocity from 2 to 4 seconds? First, elementary algebra, the average velocity, remember, is total distance over total time. Therefore, S of t sub 2, that means S of 4, minus S of t sub 1, that means S of 2 over 4 minus 2, which means we're going to plug in 4, we're going to plug in 2. The bottom is also 4 minus 2, 2. So that's 2 times 4 squared minus 5 times 4 plus 40, minus plug in 2, 2 times 2 squared minus 5 times 2 plus 40. And when you do the math, this becomes 52, this becomes 38. So 50 minus 38 is 14, divided by 2 is 7 units of the velocity, which is meters per second, or units of the numerator over units the denominator. The numerator is the change in distance. Now, that was elementary algebra. Now, what is the instantaneous velocity and acceleration of the object? What is the velocity and acceleration of the object after 6 seconds? This is calculus. So V is clearly differentiation. So V of t is S prime, which is simply 4t minus 5. Plug in 6 to find the velocity after 6 seconds. 4 times 6, 24 minus 5. That results in 19 meters per second. Acceleration, by definition, is the second derivative of the position function. A is v prime equals s double prime. So simply differentiate it again. When I differentiate this again, I get just 4, which is a constant. So I really don't have to plug in 6 because it makes no difference. Whatever the time might be, after 2 seconds, 5 seconds, 10 seconds, this is independent of t, so it's always 4. And the units are meters per square second. Why is that the case? A of t means dv dt, and this has units of meters per second. This has units of seconds, therefore meters per square second. When does the object reach a velocity of 31 meters per second? So velocity is 4t minus 5, set it equal to 31. When you do that, you move the negative 5. Make it positive 5 and 31. 36 divided by 4, 9 seconds. The height in inches of a sunflower X weeks after being planted can be approximated by this function. How tall is it in 8 weeks? By the way, any application, if units are given, you want to give them back with proper units. So obviously, part A simply is f of 8, which means replace the x with 8. That's it, elementary algebra. So 6 times 8 minus 1/4 of 8 squared. So that gives you 32 inches. This is 48. This is 64 times 1/4, 16. So we get 32. Find the average rate of growth from the end of week 6 to the end of week 12. This is elementary algebra, rise over run, f of x of 2 minus f of x of 1. That means f of 12 minus f of 6 over x of 2 minus x of 1 or 12 minus 6. So that means go to the original function, plug in 12, plug in 6, evaluate it. 6 times 12, 72 minus, this is 144, 1/4 of it is 36, so this is 72 minus 36. 6 times 6, 36, 6 squared is also 36, 1/4 of it is 9, so this is 36 minus 9, and you have to apply the negative, this becomes negative, this becomes positive, these two cancel each other with 72. So you have positive 9 over positive 6, 9 over 6 or 3/2 inches per week, units of the y over units of x. So that's in inches and this is in weeks. And now let's get to calculus. Find the instantaneous rate of growth 10 weeks after planting. Simply put, let's find f prime of x, which is 6 minus half of x. And now we plug in 10. That gives you 5. So 6 minus 5 is 1. So f prime of 10 is 6 times minus 1/2 times 10. This is 5. Let's change it to 5. So this means 5. And that's 1. And the units, 1 inch per week, everybody. And what does it mean? On week 10, the sunflower is growing at a rate of 1 inch per week. That's the meaning of it. Exponential growth and decay. A quantity q equals q of t or y equals y of t is said to have an exponential growth or decay model if it increases or decreases at the rate that is proportional to the amount of the quantity present. So dy dt is ky, y is c e to the power of kt, or instead of c, we can say y of 0 or y sub 0. These are different ways of representing the same thing depending on the text and the concept that you're using. For example, everybody remembers a equals p e to the power of rt, that it's a compounding. Dealing with money, normally we use that. That's a continuous compounding. So they all really mean the same thing. In some texts, instead of that, they may use p equals p sub 0 e to the power of rt, and either r or k. C is the initial value. K or r, constant of proportionality, relative growth rate. Whereas dp dt equals kp is rate of growth or growth rate. So relative growth rate, but with growth rate are different. So this equation 1 that we have here is sometimes called the law of natural growth if k is positive, or the law of natural decay if k is negative. It is called a differential equation because it involves an unknown function y and its derivative dy dt. So dy dt is ky, dy dt is minus ky. Sometimes they just keep the negative sign in front of k. But the bottom line is the exponent will be positive in the case of exponential growth, negative otherwise. So let's actually show that if y equals c e to the power of kt, and I want to differentiate that. Y prime or dy dt, remember, it's itself c times e to the power of kt times k. So I hope everybody's okay with differentiation. So one more time, is an exponential function. Differentiation C is a multiplier, is a coefficient remains. E to the power of kt is itself times k. Okay. So what is this one? Same thing, y. So dy dt is y times k or ky. That's exactly what we had here. So we prove that this is the solution. We also have what's known as the Newton's law of cooling. Dt is k times T minus T sub s. This capital T represents the temperature. This lowercase t represents time. And according to that, we get T of t equals y sub 0 e to the power of kt plus T sub s. And y sub 0 is T sub 0 minus T sub s. We're going to look at this with more details shortly. But for now, let's look at this example where a population of bacteria grows from 1,000 to 4,000 in 3 hours. Assume exponential growth. Find the population in 6 hours. And there are different ways of approaching that. Just reminding you of this formula, y equals c e to the power of kt. And again, please understand this is the initial value, y of 0 or y sub 0. Reminding you ln of e to the power of x is x, e to the power of ln x is x, because we're going to use that. So let's see what happens here. So what is given? The formula is that where the initial value is 1,000 and y in 3 hours at t equals 3, we get 4,000. First, that is the given. So understanding what's given. So we are going to do what here? First and foremost, we need to find k. In other words, we have to find this formula. To find this formula, we need to find k. And then t equals 6, plug in 6. So first find k, and then y of t is known and evaluated at t equals 6. So, all right, so in this formula, we are going to replace the c with what is given, and we get y of t equals 1,000 e to the power of kt. Also, we know y of 3 is 4,000. So in this formula, we replace the t with 4,000. So we get 1,000 e to the power of k times t, and t equals 3. Now, obviously, we are going to drop the 1,000, right? And this becomes 4 because we are dividing both sides by 1,000. Now we're going to take, because the base is e, we're going to take a natural log of that. So we're going to take a natural log of both sides. And ln of e to the power of x is x. That means this is 3k. This is ln 4. And so what is k? Ln 4 divided by 3. Now you can keep it as that. This is an exact answer if you go with a bunch of decimals, such as 0.4621, however many decimals. The more, the better. And so we have the formula for y of t, and it's 1,000 e to the power of 0.4621 t. So that's what we have. And so what is y of 6? Then replace the t with 6. Putting it into a calculator gives us a number. And because we are dealing with the number of bacteria, we're going to round it accordingly. So this one becomes 16,000 because we are looking at the number of bacteria. Again, number of bacteria versus number of bacteria per unit of time, that's different. That one, you don't have to do that. There is another way in this case that you may be able to evaluate in no time. Notice, from 1,000 to 4,000 in 3 hours, that means it got 4 times. And in 6 hours, it's going to get 4 times again. That's 4 times 4,000 is 16,000. So again, you may see it that way, and by all means. Now, of course, I want to remind you that we could go back here, keep it as ln 4 over 3, and see how it looks like. So y of t is, I'm going to go back here and use this one, 1000 e to the power of, instead of approximation, I want to go with ln 4 over 3. And the fact that e to the power of ln x is x, I'm going to put e to the power of ln 4. And then, in other words, ln 4 over 3 times t is ln 4 times 1/3 of t, or t over 3. Let me just show you what I mean. This is the product of ln 4 and t divided by 3. And e to the power of ln 4 is simply 4. So if you go this route, and now replace the t with 6, you get 6/3, which is 2. That's 4 squared, 16 times 1000. That gives you exactly the same answer. So this happened to give you an exact answer because we didn't use the approximation. Okay, I just wanted you to be aware of that, everybody. So there is a way to come up with an exact answer. You just want to make sure that you're comfortable with the process and handling the algebra behind that, which is not a big deal. All right. When will the population reach this number? Well, we're going to write y of t equals 30,000. And you really can go with any of them. Okay, for example, if you go with this one, obviously we start dropping the 1000 at this becomes 30. In other words, divide by 1000. So you get 30 equals e to the power 0.4621, and we're going to take a natural log of both sides. Left side becomes ln 30, and the right side, ln of e to the power 0.4621t, it just remains the exponent. And therefore, t is the left side, ln of 30 divided by this number, which is 0.4621. And with a bunch of decimals, you get 7.3603 hours. In this case, won't make that much of a difference if you go with the exact answer, but that works too. So this would be the answer here. Exponential decay model. Physicists express the rate of decay in terms of half-life, the time required for half of any given quantity to decay. Generally speaking, m of t is m sub 0 e to the power of kt. Y equals c e to the power of kt. Half-life, h is minus ln 2 over k is minus ln 2 over h, and h is ln 2 over k. This can be shown, and I'm going to go over that in a moment, but let's look at this example. A sample contains 1 gram of radium. How much radium will remain after 1,000 years? Use a half-life of 1,620 years. So we are using y equals c e to the power of kt. Initially, we have this much. That means c, or y of 0, is 1. And the half-life is 1620. And we want to know y after t equals 1000. So that is the explanation of the question symbolically. So let's show the concept of a half-life and how we arrive at the answers here. So starting with y equals c to the power of kt, half-life. You don't even have to know what is the initial value, which happened to be 1 gram. So just if you want half-life, that means the amount of time it takes that the initial value to go to half of it. What is the initial value c? What is half of it? 1/2 c. And I hope you see why it's not important what's the initial amount, because it will drop from both sides. And now if you take the natural log of both sides, why natural log? Because this one has a base e, and the left side is ln1 minus ln2, the right side is kt. I hope everybody knows ln1 is 0. So kt is minus ln2. If you solve for t, you get minus ln2 over k. If you solve for k, you get minus ln2 over t. And as I said, for t, minus ln2 over k. And that's exactly what we had here. So in this case, we proved that's the way you find k. And so if that is the case, we are going to go with negative ln2, okay, over the half-life, which is 1620. Again, that's an exact answer. An approximation with a bunch of decimals becomes roughly, it's an approximation, minus 0.000427. As far as the number of decimals is concerned, you really have to be very careful. You want to carry as many decimals as possible, especially in intermediate steps, okay? Otherwise, the final answer will be way off. And so y of t becomes c, which happened to be 1. So I then write it, e to the power of this number times t. And so how much will remain after 1,000? So replace the t with 1,000, everybody. Put it into a calculator, gives you almost 0.652 grams. Because this was 1 gram, obviously we use the same units. The growth in world population in millions is estimated by the formula P of t is 8,200 e to the power of 0.011 t, where t is the number of years since 2025. Find the instantaneous rate of change for the year 2050, include units. Well, instantaneous rate of change. Let's differentiate this. So we want P prime of t. To differentiate this, obviously we need 8,200, and then exponential is itself, and then by the chain rule, the derivative of e to the power of kx is itself times k, so times this number in front of t. And we're going to put these two together by multiplying the two and put it in front, and p prime of t becomes 9. The product of these two is 90.2 e to the power of 0.011 t. So the difference between the two is the time of interest, which is 25, and we are going to replace the t with 25. That means the p prime of 25. It's 118.7511. Remember, p prime, that means dp dt, the change in population over change in time. So millions of people per year. That's how you arrive at the units. Again, this is dp. Let me just write that. So p prime is dp dt, change in population over change in time. That's why you have the units. So what does that mean? 118.7511 million. That means 118,751,100 people per year. So in 2050, the world population will be increasing at this rate, 118,751,100 people per year. As far as a slightly different method to evaluate this class, remember y equals c to the power of kt, dy dt is ky, rate of growth is dp dt, and relative growth rate is k, which is from here 0.011. So we should know those numbers. And so we are interested in finding a p prime of 25. So according to this concept, it's simply dp dt is kp. So kp at t equals 25. So k obviously is 0.011, and then times this one, where t, of course, is replaced with 25. So 0.011, same thing, and t is replaced, and you get exactly the same answer as you are supposed to. just in case. All right, and now Newton's law of cooling. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surrounding, provided that this difference is not too large. This law also applies to warming. The concept is this: you have a cold drink, cold soda, you bring it to a room, it ultimately takes the room temperature over the course of some time, maybe so many hours. On the other hand, if you have a hot cup of coffee, you bring it to a room, it will cool down in the same manner. So if we let capital T of T be the temperature of the object at time lowercase t, and T sub S be the temperature of the surrounding, then we can formulate Newton's law of cooling as a differential equation. dt is K times T times minus T sub S. T sub S is the surrounding temperature. K is constant. So let's look at this and see what happens here. So we're going to write dt. That means T. Let me just write this in this fashion so it makes it easier to understand. When we say dt, we mean T prime of T, capital T prime of T. That's the meaning of it. Okay. And so this is K times something. This is T, capital T, the temperature as a function of T. Okay, so let me just make sure that we understand what's going on here. When we say T, we mean T as a function of lowercase t. That's the meaning of it, okay? I'm going to come back and erase that in a moment. And when we say dt, we mean T prime of T. And let me erase this one. Okay, so that's, just want to make sure we understand that. So now let's call this function T of T minus T sub S something. For example, Y as a function of T. So if this is Y, then this is K times Y. Okay. So if Y is capital T minus T sub S, let's differentiate both sides, and Y gives you Y prime, T gives you T prime, T sub S. The surrounding temperature is a number, gives you 0. So what does it mean? That means Y prime and T prime are the same. Their derivative is the same. The two functions are not the same. They vary by a constant. So this is Y prime or dy dt. This is T prime or dt dt. Okay, so let's write it in that fashion. So according to this then, dy dt, this is dt dt, everybody. This is capital dt dt. And we prove dt dt is dy dt. So if I replace it here, take a look at these two equations. So instead of dt dt, I'm going to put dy dt. So dy dt is ky. I hope everybody is following that. Now let me erase my work. I need this space. So dy dt is dt dt or ky. And if we look at these two, dy dt is ky. Go back here. So y is y sub 0 e to the power of kt. Please understand, c or y of 0 or y sub 0, they all refer to the initial value. Remember, if you replace this with 0, y of 0 becomes y sub 0. Okay, so going back to this one, we said y is this. Y of t is T of T minus T sub S. And it's equal to that. So Y of T is T of a T minus T sub S. and it's equal to y sub 0 e to the power of kt again. All right. And so if I move the t sub s and make it positive on the other side, I get the formula for t of t. Capital T of t is y sub 0 e to the power of kt plus t sub s. So their difference is just a constant. And now, as far as the initial value is concerned, okay, if I replace the t with 0, I get y sub 0 e to the power of 0 plus t sub s. And as you know, e to the power of 0 is 1. So look at this one. T of 0 is y sub 0 plus t sub s. So y sub 0, if I move the t sub s, becomes t sub 0 minus t sub s. Very straightforward. I hope everybody is okay with that. Again, let me erase my work. Here's the final result. We proved, believe it or not, that T of t, capital T of t, is y sub 0 e to the power of kt plus t sub s, where y sub 0 is t sub 0 minus t sub s. And even if you don't remember that, just replace the t with 0 and this comes to you, class. Again, what is the value of y sub 0? I don't know. Plug in 0. Okay? And you'll see that. It's that simple. Let's look at a very simple example. A 180-degree turkey is removed from the oven and placed in a 74-degree Fahrenheit room. After 15 minutes, it has cooled down to 136 degrees Fahrenheit. Find the general solution for T. Plus, even for your homework assignments or exam, I expect this to happen before we answer. If it has several parts, you have to come up with T of t to make sure you can move on. It's important to do that. So we have this one. So let's see what is given. I hope you realize this one as the initial temperature, 180 degrees, is T sub 0. We bring it to the room, that is the surrounding temperature, T sub s. 15 minutes, T of capital T of 15 is 136. So this is given, everybody. So we are going to go with this formula and write T of t. To do that, we are going to go with y sub 0 is T sub 0 minus T sub s, or T of 0 minus T sub. So the difference between the two, or 106, is y sub 0. And writing this formula, we are going to say T of t is 106 e to the power of kt plus T sub s, 74. So as you can see, we have most everything. What is missing is k. So we need to find the k, and there is one more piece of information here. T of 15 is 136. So right here, T of 15 is 106 e to the power of k times 15 plus 74 equals 136. Subtract 74 and we get 62 on the right side. Divide both sides by 106. In fact, I'm going to keep it as 62 over 106, although it will simplify, okay, to 31 over 53. I don't want to do that yet. In order to get to k, we're going to take a natural log of both sides. The left side becomes 15k, the right side remains unchanged, and therefore k is the right side, ln of 62 over 106, divided by 15. And now we put it into a calculator and we use a bunch of decimals. K becomes roughly negative 0.035754. And therefore, now we go back here and we write capital T of t is 106 e to the power of k, replace it, times T plus 74. So we have the answer. Now, what I want to do, I want to show you a slightly different method of approaching that. So I want to go to this one and simplify it to 31 over 53. And I'm interested, going back to this, I'm interested in e to the power of k. So I'm going to replace e to the power of k with something. So all I have to do, how do I get rid of 15? Raise this to the power of 1 over 15. Take a look, class. If I raise this to the power of 1 over 15, I hope you see it becomes e to the power of k. So if that is e to the power of k, what is e to the power of kt? Raise both sides. Now raise this one to the power of t, this one to the power of t, and this becomes e to the power of kt. Let me just do this in this fashion. Let's see what color do I want to use. I raise this to the power of t, this one to the power of t, and we get e to the power of k. T is 31 over 53, t over 15. So I want to go back here and say t of t is 106, e to the power of kt. So solve for e to the power of kt, replace it with this, plus 74. Does it make any difference here? Not much, okay? So I'm going to write for the, we're going to continue. This is the same question for part B. What is the Turkish temperature after 60 minutes? I'm going to write both equations we got. This is what I mean. The question is really about like part B, but you have to come up with the general solution anyways. And so having said that, here's what happens. I can use either one. But if I put it here, because 60 is divisible by 15, gives you a little bit more precise answer, class. So this is obviously 4. So you raise 31 over 53 to the power of 4 times 106 plus 74, and you get 86.4065 degrees Fahrenheit. This number, as you raise it to power, gets even smaller. You know that. How long will it take to get to 110 degrees Fahrenheit? Set one of them, doesn't matter which one equals 110. For example, let's work on this one now. And obviously, we are going to first move the 74. We get 36. Obviously, we're going to divide both sides by 106. Because when I get to t, we're going to take a natural log of both sides. When you take the natural log of both sides, the right side remains unchanged. The left side becomes just the exponent, negative 0.035754. Divide by this number. Let me just actually erase my work. Just divide by negative 0.035754. And that gives you roughly 30.2, about 30 minutes. But as far as the number of decimals, you always want to go with many decimals. You want to follow what they ask you. Okay. All right, put on your detective caps. A dead body was found at 1:30 a.m. when the temperature was 55 degrees Fahrenheit and the body temperature was 87 degrees Fahrenheit. Remember, normal body temperature is 98.6 degrees Fahrenheit, roughly, which is nowadays is this feeling. 1 hour later, the body had cooled down to 85. So from 87, now that's what they do. As soon as they find the body, they take the temperature and then they wait some time and then they do it again. And that will give them a chance to use, for example, Newton's law of cooling to figure out the time of death. Of the 3 suspects, SpongeBob had an alibi until 12 a.m. Mickey Mouse had an alibi between 7 and 10 p.m. And Goblin had an alibi for 10 p.m. and after. Who has a good alibi? Okay. We really want to know what's going on, so we are going to go back and read it again. We're going to say in the beginning, because at 1:30 a.m. at t equals 0, which is 1:30 a.m. Okay. What is this? Temperature is 55 degrees Fahrenheit. That is the surrounding temperature. And the initial temperature, T sub 0, is 87. And then 1 hour later, you can go with hour or minutes. Perhaps minutes is, gives us better because we have it in this format, but it doesn't really make much of a difference. So T of 60 is 85. So this is the given. So how do we deal with this? We are going to find out at what time it is supposed to be a normal temperature of 98.6. So T, let's find out, T of what time should be the normal temperature of 98.6? Well, we are going to use the Newton's law of cooling, and T sub 0 is 87 minus T sub S is 55, so we get 32. Therefore, we are going to write this T of t is y sub 0, which is 32 e to the power of kt, plus T sub S, which is 55. So we write the equation. As you can see, most everything is in good shape. What is missing in action is k. We need to find the k. T of 60 equals 85 will help us find the k. So T of 60, that means 32 e to the power of k times 60 plus 55 must be 85. So the first thing we do, we subtract 55 from both sides. And we get 32 e to the power of k times 60 is 30. We are going to divide both sides by 32 because we want to find the k, which is the part of the exponent. We take the natural log of both sides because on the left side, the base is e. And of course, the left side is just the exponent, 60k. And so k is the right side, ln of 30 over 32 divided by 60 precisely. Putting it into a calculator results in this number, negative 0.001075. So we are going to go back to T of t and write T of t is 32 e to the power of k, which is this number, times t plus 55. So we found the general solution. Now we need to find when T of what time should be 98.6. So set this equal to 98.6. So we set this equal to 98.6. So the very first thing, obviously, we are subtracting 55 from both sides. And 98.6 minus 55 is 43.6. We are going to divide both sides by 32. We're going to take a natural log of both sides. And the left side becomes just the exponent. The right side doesn't change. So what is t is the right side divided by the coefficient of t, negative 0.001075. So this is the exact answer. To answer this, we're going to put into calculator and we get roughly negative 287.7, almost 288 minutes negative. What does it mean? That means 288 minutes before 1:30 it happened. So 1:30 a.m. subtract 288 becomes 8:42. And I want you to recognize, never mind 288, 300 minutes is 5 hours. So 1:30 minus 5 hours is 8:30. So it's easy to calculate. You see that this becomes so 8:42 roughly. Okay. So let's go back. SpongeBob and an alibi until 12 a.m. So SpongeBob is in good shape. Mickey Mouse, 7 to 10, in good shape. Goblin and an alibi for 10 p.m. and after, just after 10 p.m. Clearly, we found the killer.